In this class, we study discrete-time dynamical system used in economics, and the reference is Stokey-Lucas-Prescott, Chapter 6. So let's start with the simplest dynamical system. Kt plus 1 equal A times Kt plus B. K can be any variable, can be saving, capital, price, whatever. And the equation says the next state value of K is equal to constant A times the current value of K, Kt, plus another constant B. And this rule applies for all T. This is a first order difference equation because Kt plus 1 is determined only by Kt. It doesn't refer to order dates such as Kt minus 1 or T minus 2. And this is linear. Kt plus 1 is a linear function of Kt. There is no Kt squared or log of Kt. It is not homogeneous due to this constant term B, but it is linear in the sense that it is affine. Finally, this system is autonomous in the sense that the rules of transition do not depend on calendar time t, because both A and B are constant. This is an example of a non-autonomous system, Kt plus 1 equal 0.5 Kt plus 2 to the power t. Okay, so this part depends on calendar time t, so the rule of transition is time variant, and in that case the system is said to be non-autonomous. Equation 1 is an autonomous system. Now, this system has a unique stationary point which we denote by k-bar unless A is equal to 1. Instead of stationary point, I sometimes use the words fixed point, steady state. They all mean the same. What is meant by a stationary point k-bar is that if the current value of k is k-bar, then tomorrow is going to be the same. Okay? If today is k-bar, then tomorrow will be also k-bar. So essentially equation 2 is the definition of a stationary point or fixed point or steady state. And this equation implies that k-bar is equal to b over 1 minus a. So as long as a is different from 1, this equation has a unique solution for k-bar. Now I will show you a small technique that is always used. Let's subtract this equation 2 from equation 1. Okay, we have Kt plus 1 minus k-bar equal A times Kt minus k-bar, and B is cancelled out. So as a result, we have Kt plus 1 minus k-bar equal A times Kt minus k-bar. Basically, by subtracting the equation that characterizes a fixed point from the original system, we can make a non-homogeneous difference equation homogeneous by considering the deviation from a fixed point, so that the next date deviation from the stationary point is equal to A times the current date deviation from the stationary point. Okay, by multiplying A, you can get the next date deviation from the stationary point. Well, then it follows that starting with the initial date deviation, the deviation at the initial date, k0 minus k-bar, you just multiply A t times and you'll get the date t deviation from the stationary point, kt minus k-bar. Once you get this expression, you can understand the dynamics of this system. If A is smaller than 1 in absolute value, then Kt minus k-bar will become smaller and smaller, and it will eventually converge to 0. In other words, Kt will eventually converge to the stationary point k-bar. In contrast, if A is larger than 1 in absolute value, then Kt minus k-bar will diverge, either to plus infinity or minus infinity. In other words, Kt will move farther and farther away from the stationary point k-bar. This first diagram shows the dynamics of this system, equation 1, when the slope A is smaller than 1. So the horizontal axis is kt and the vertical axis is the next date value of k, kt plus 1. This purple line represents the system, kt plus 1 equal a kt plus b. The slope is smaller than 1. And the stationary point of this system is represented by the intersection between this line and the 45-degree line. Suppose the system starts with this value, k0. If k0 is here, then k1 is here, according to this line. So k1 would be around here. If k1 is here, then according to this line, k2 will be around here. So because this is the 45-degree line, this means that k2 is around here. And then k3, k4, you can visually see that kt will converge to k bar. Now suppose that the slope variable a is larger than 1, so that the line is much steeper. Again, the stationary point is the intersection with the 45-degree line. So you can see that if the system starts with a value that is exactly equal to k bar, then the next state will remain k bar, k bar, k bar, k bar, k bar. It's constant. It stays there. It's steady state. But as you can see, if the system starts with a value that is even slightly different from k bar, then it will not converge to k bar. If the initial value k0 is, let's say, here, then k1 is, according to this line, k1 is around here, and then k2 is around here, k3 is around here, so it will diverge. Let me summarize. We studied the dynamics of a first-order linear autonomous system. If A is smaller than 1 in absolute value, then the system will converge to the unique stationary point or steady state k bar. If A is larger than 1 in absolute value, then the system diverges. Okay? Now, even if there are more than one variable, let's say there are two variables, if each variable is autonomous, then the story is the same. Suppose we have x as well. So kt plus 1 is equal to ak plus b, this is the same. And xt plus 1 is equal to cxt plus d. They are separately autonomous because k doesn't depend on x and x doesn't depend on k. To put it in a different way, if you express this system of difference equations in a matrix form, then the coefficient matrix will be a diagonal matrix, so that the off-diagonal elements are 0. In this case, the story is the same, right? Because we can analyze k and x separately. If a is smaller than 1, then k will converge to the stationary point k bar. If c is smaller than 1, then x will converge to the stationary point x bar. Now, the case that the variables are not separately autonomous looks like this. So kt plus 1 is determined not only by kt but also xt, and xt plus 1 is determined not only by the previous value xt but also by kt. Why do I say that this is not separately autonomous? Well, if you just look at the first equation, if you look at the dynamics of k, the rules of transition depend on something that is time variant. Okay? So this system is time dependent. If you look at the transition of x, again, x is determined not only by the previous value of itself, but also something else that depends on t. So this is not autonomous. If you look at k and x together, okay, k and x together follows a time-independent, time-invariant system, but they are not separately autonomous. In order to study the dynamics in such a case, we cannot simply look into the sides of A and the sides of C. how to study dynamics is a little bit more complicated. It's not too complex, but it's a little more complex, and we will study how to deal with it in one of the later classes. So here is our plan for the subsequent classes. We've just studied the most basic case, the linear first-order autonomous system. Now we are ready to study three important extensions, three important techniques. First, we'll study how to make a nonlinear system linear by means of linear approximation. Second, we'll study how to deal with a higher order system, how to convert a higher order system into a first order system. And the method is the variable stacking. And then we'll study how to deal with a system with more than one variable, in which the variables are dependent on each other. A multivariable system in which this coefficient matrix is not a diagonal matrix. And the method is diagonalization. Okay, that's our plan.